Hello, this is Teacher Todd. We will now continue with Network Security Essentials. We're on to Chapter 9, which is IP security. We'll start out with an IP security overview. In 1994, the Internet Architecture Board, IAB, issued a report titled Security in the Internet Architecture, RFC 1636. The report identified key areas for security mechanisms. Among these were the need to secure the network infrastructure from unauthorized monitoring and control of network traffic, and the need to secure end-user to end-user traffic using authentication and encryption mechanisms. To provide security, the IAB included authentication and encryption as necessary security features in the next generation IP, which has been issued as IP version 6. Fortunately, these security capabilities were designed to be usable both with the current IP version 4 and future IP version 6. This means that vendors can begin offering these features now, and many vendors now do have some IPsec capability in their products. The IPsec specification now exists as a set of Internet standards. Applications of IPsec. IPsec provides the capability to secure communications across a LAN, across private and public WANs, and across the Internet. Examples of its use include secure branch office connectivity over the Internet. A company can build a secure virtual private network over the Internet or over a public WAN. This enables a business to rely heavily on the Internet and reduce its need for private networks, saving costs and network management overhead. Secure remote access over the Internet. An end user whose system is equipped with IP security protocols can make a local call to an Internet Service Provider, ISP, and gain secure access to a company network. This reduces the cost of toll charges for traveling employees and telecommuters. Establishing extranet and intranet connectivity with partners. IPsec can be used to secure communication with other organizations, ensuring authentication and confidentiality, and providing a key exchange mechanism. Enhancing electronic commerce security. Even though some web and electronic commerce applications have built-in security protocols, the use of IPsec enhances that security. IPsec guarantees that all traffic designated by the network administrator is both encrypted and authenticated, adding an additional layer of security to whatever is provided at the application layer. The principal feature of IPsec that enables it to support these varied applications is that it can encrypt and/or authenticate all traffic at the IP level. Thus, all distributed applications, including remote logon, client server, email, file transfer, web access, and so on, can be secured. An IPsec VPN scenario. The figure shows a simplified packet format for an IPsec option known as tunnel mode, described subsequently. Tunnel mode makes use of an IPsec function, a combined authentication encryption function called encapsulating security payload, ESP, and a key exchange function. For VPNs, both authentication and encryption are generally desired because it is important to both 1. Assure that the unauthorized users do not penetrate the VPN, and 2. Assure that eavesdroppers on the Internet cannot read messages sent over the VPN. The figure is a typical scenario of an IPsec usage. An organization maintains LANs at dispersed locations. Non-secure IP traffic is conducted on each LAN. For traffic outside, through some sort of private or public WAN, IPsec protocols are used. These protocols operate in networking devices, such as a router or firewall, that connect each LAN to the outside world. The IPsec networking device will typically encrypt all traffic outgoing to the WAN and decrypt traffic coming from the WAN. These operations are transparent to the workstations and servers on the LAN. Secure transmission is also possible with individual users who dial into the WAN. Such user workstations must implement the IPsec protocols to provide security. Benefits of IPsec. Some of the benefits of IPsec include the following. When IPsec is implemented in a firewall or router, it provides strong security that can be applied to all traffic crossing the perimeter. Traffic within a company or work group does not incur the overhead of security-related processing. IPsec in a firewall is resistant to bypass if all traffic from the outside must use IP and the firewall is the only means of entrance from the internet into the organization. IPsec is below the transport layer, TCP/UDP, and so is transparent to all applications. There is no need to change software on a user or server system when IPsec is implemented in the firewall or router. Even if IPsec is implemented in end systems, upper layer software, including applications, is not affected. IPsec can be transparent to end users. There is no need to train users on security mechanisms, issue keying material on a per-user basis, or revoke keying material when users leave the organization. IPsec can provide security for individual users if needed. This is useful for off-site workers and for setting up a secure virtual subnetwork within an organization for sensitive applications. Routing applications. In addition to supporting end users and protecting premises systems and networks, IPsec can play a vital role in the routing architecture required for internetworking. The following is a list of some examples of the use of IPsec. IPsec can assure that a router advertisement, a new router advertises its presence, comes from an authorized router. A neighbor advertisement, which is a router seeking to establish or maintain a neighbor relationship with a router in some other routing domain, comes from an authorized router. A redirect message comes from the router to which the initial IP packet was sent, and a routing update is not forged. Without such security measures, an opponent can disrupt communications or divert some traffic. Routing protocols such as Open Shortest Path First, OSPF, should be run on top of security associations between routers that are defined by IPsec or have some other security protection. IPsec documents. IPsec encompasses three functional areas: authentication, confidentiality, and key management. The totality of the IPsec specification is scattered across dozens of RFCs and draft IETF documents, making this the most complex and difficult to grasp of all IETF specifications. The best way to grasp the scope of IPsec is to consult the latest version of the IPsec document roadmap, which is RFC 6071, IP Security, IPsec, and Internet Key Exchange, IKE, document roadmap. The documents can be categorized into the following groups. Architecture covers the general concepts, security requirements, definitions, and mechanisms defining IPsec technology. The current specification is RFC 4301, Security Architecture for the Internet Protocol. Authentication Header, AH. AH is an extension header to provide message authentication. The current specification is RFC 4302, IP Authentication Header. Because message authentication is provided by ESP, the use of AH is deprecated. It is included in IPsec version 3 for backward compatibility, but should not be used in new applications. We do not discuss AH in this chapter. Encapsulating security payload, ESP. ESP consists of an encapsulating header and trailer used to provide encryption or combined encryption authentication. The current specification is RFC 4303, IP Encapsulating Security Payload, ESP. Internet Key Exchange, IKE. This is a collection of documents describing the key management schemes for use with IPsec. The main specification is RFC 7296, Internet Key Exchange, IKE version 2 protocol. But there are a number of related RFCs. Cryptographic algorithms. This category encompasses a large set of documents that define and describe cryptographic algorithms for encryption, message authentication, pseudorandom functions, and cryptographic key exchange. There are a variety of other IPsec-related RFCs, including those dealing with security policy and management information-based content. IPsec services. IPsec provides security services at the IP layer by enabling a system to select required security protocols, determine the algorithms to use for the services, and put in place any cryptographic keys required to provide the requested services. Two protocols are used to provide security. An authentication protocol designated by the header of the protocol, authentication header, AH, and a combined encryption authentication protocol designed by the format of the packet for that protocol, encapsulating security payload, ESP. RFC 4301 lists the following services: access control, connectionless integrity, data origin authentication, rejection of replayed packets, which is a form of partial sequence integrity, confidentiality, which is encryption, limited traffic flow confidentiality. Transport and tunnel modes. Both AH and ESP support two modes of use, transport and tunnel mode. The operation of these two modes is best understood in the context of a description of ESP, which is covered in section 9.3. Here we provide a brief overview. Transport mode provides protection primarily for upper layer protocols. That is, transport mode protection extends to the payload of an IP packet. Examples include a TCP or UDP segment or an ICMP packet, all of which operate directly above IP in a host protocol stack. Typically, transport mode is used for end-to-end communication between two hosts. For example, a client and a server, or two workstations. When a host runs AH or ESP over IP version 4, the payload is the data that normally follow the IP header. For IP version 6, the payload is the data that normally follow both the IP header and any IP version 6 extension headers that are present, with the possible exception of the destination options header, which may be included in the protection. ESP in transport mode encrypts and optionally authenticates the IP payload, but not the IP header. AH in transport mode authenticates the IP payload and selected portion of the IP header. Tunnel mode provides protection to the entire IP packet. To achieve this, after the AH or ESP fields are added to the IP packet, the entire packet plus security fields is treated as the payload of the new outer IP packet with a new outer IP header. The entire original inner packet travels through a tunnel from one point of an IP network to another. No routers along the way are able to examine the inner IP header. Because the original packet is encapsulated, the new, larger packet may have totally different source and destination addresses, adding to the security. Tunnel mode is used when one or both ends of a security association, such as a security gateway or a firewall or a router, that implements IPsec. With tunnel mode, a number of hosts on networks behind firewalls may engage in secure communications without implementing IPsec on their own. The unprotected packets generated by such hosts are tunneled through external networks by tunnel mode SAs, set up by the IPsec software in the firewall or secure router at the boundary of the local network. ESP in tunnel mode encrypts and optionally authenticates the entire inner IP packet, including the inner IP header. AH in tunnel mode authenticates the entire inner IP packet and selected portions of the outer IP header. Tunnel mode and transport mode functionality table. Please pause this and review the attached table. IPsec architecture. Fundamental to the operation of IPsec is the concept of a security policy applied to each IP packet that transits from a source to a destination. IPsec policy is determined primarily by the interaction of two databases, the Security Association Database, SAD, and the Security Policy Database, SPD. This section provides an overview of these two databases and then summarizes their use during IPsec operation. The figure illustrates the relevant relationships. Security Association, SA. A key concept that appears in both the authentication and confidentiality mechanisms for IP is the Security Association SA. An association is a one-way logical connection between a sender and a receiver that affords security services to the traffic carried on it. If a pure relationship is required to be two-way and secure, then two security associations are required. A security association is uniquely identified by three parameters. Security Parameters Index, SPI, a 32-bit unsigned integer assigned to this SA and having local significance only. The SPI is carried in AH and ESP headers to enable the receiving system to select the SA under which a received packet will be processed. IP destination address. This is the address of the destination endpoint of the SA, which may be an end-user system or a network system, such as a firewall or router. Security Protocol Identifier. This field from the outer IP header indicates whether the association is an AH or ESP security association. Hence, in any IP packet, the security association is uniquely identified by the destination address in the IP version 4 or IP version 6 header, and the SPI in the enclosed extension header, AH or ESP. Security Association Database, SAD. In each IPsec implementation, there is a nominal security association database that defines the parameters associated with each SA. A security association is normally defined by the following parameters in an SAD entry. Security Parameter Index, a 32-bit value selected by the receiving end of an SA to uniquely identify the SA. In an SAD entry for an outbound SA, the SPI is used to construct the packet's AH or ESP header. In an SAD entry for an inbound SA, the SPI is used to map traffic to the appropriate SA. Sequence number counter, a 32-bit value used to generate the sequence number field in AH or ESP headers, described in the section 9.3, required for all implementations. Sequence counter overflow, a flag indicating whether overflow of the sequence number counter should generate an auditable event and prevent further transmission of packets on this SA, and this is required for all implementations. Anti-replay window, used to determine whether an inbound AH or ESP packet is a replay, which is described in section 9.3, and this is required for all implementations. AH information, authentication algorithm, keys, key lifetimes, and related parameters being used with AH, and this is required for all AH implementations. ESP information, encryption and authentication algorithm, keys, initialization values, key lifetimes, and related parameters being used with ESP, and this is required for ESP implementations. Lifetime of this security association, a time interval or byte count after which an SA must be replaced with a new SA and a new SPI. Otherwise, it must be terminated. Plus, it must include an indication of which of these actions should occur. And this functionality is required for all implementations. IPsec protocol mode, tunnel, transport, or wildcard. Path MTU, any observed path maximum transmission unit, maximum size of a packet that can be transmitted without fragmentation, and aging variables. This is required for all implementations. The key management mechanism that is used to distribute keys is coupled to the authentication and privacy mechanisms only by way of the Security Parameters Index, SPI. Hence, authentication and privacy have been specified independently of any specific key management mechanism. IPsec provides the user with considerable flexibility in the way in which IPsec services are applied to IP traffic. As we will later see, SAs can be combined in a number of ways to yield the desired user configuration. Furthermore, IPsec provides a high degree of granularity in discriminating between traffic that is afforded IPsec protection and traffic that is allowed to bypass IPsec, as in the former case relating IP traffic to specific SAs. Security Policy Database, SPD, the means by which IP traffic is related to specific SAs, or no SA in the case of traffic allowed to bypass IPsec, is the nominal security policy database. In its simplest form, an SPD contains entries, each of which defines a subset of IP traffic and points to an SA for that traffic. In more complex environments, there may be multiple entries that potentially relate to a single SA or multiple SAs associated with a single SPD entry. The reader is referred to the relevant IPsec documents for a full discussion. Each SPD entry is defined by a set of IP and upper layer protocol field values called selectors. In effect, these selectors are used to filter outgoing traffic in order to map it to a particular SA. Outbound processing obeys the following general sequence for each IP packet. 1. Compare the values of the appropriate fields in the packet, the selector fields, against the SPD to find a matching SPD entry, which will point to 0 or more SAs. 2. Determine the SA, if any, for this packet and its associated SPI. 3. Do the required IPsec processing, for example, AH or ESP processing. SPD entries. The following selectors determine an SPD entry. Remote IP address. This may be a single IP address, an enumerated list or range of addresses, or a wildcard mask address. The latter two are required to support more than one destination system sharing the same SA, for example, behind a firewall. A local IP address. This may be a single IP address, an enumerated list or range of addresses, or a wildcard mask address. The latter two are required to support more than one source system sharing the same SA, for example, behind a firewall. Next layer protocol. The IP protocol header, IP version 4, 6, or version 6 extension, includes a field. Protocol for IP version 4, next header for IP version 6 or IP version 6 header, that designates the protocol operating over IP. This is an individual protocol number, any, or for IP version 6 only, opaque. If AH or ESP is used, then this IP protocol header immediately precedes the AH or ESP header in the packet. Name, a user identified from the operating system. This is not a field in the IP or upper layer headers, but is available if IPsec is running on the same operating system as a user. Local and remote ports. This may be individual TCP or UDP port values, an enumerated list of ports, or a wildcard port. Host SPD example. The table provides an example of an SPD on a host system as opposed to a network system such as a firewall or router. This table reflects the following configuration. A local network configuration consists of two networks. The basic corporate network configuration has the IP network number 1.2.3.0/24. The local configuration also includes a secure LAN, often known as a DMZ, that is identified as 1.2.4.0/24. The DMZ is protected from both the outside world and the rest of the corporate LAN by firewalls. The host in this example has the IP address 1.2.3.10, and it is authorized to connect to the server 1.2.4.10 in the DMZ. The entries in the SPD should be self-explanatory. For example, UDP port 500 is the designated port for IKE. Any traffic from the local host to a remote host for purposes of an IKE exchange bypasses the IPsec processing. Processing model for outbound packets. The figure highlights the main elements of IPsec processing for outbound traffic. A block of data from a higher layer such as TCP is passed down to the IP layer and an IP packet is formed, consisting of an IP header and an IP body. Then the following steps occur. 1. IPsec searches the SPD for a match to this packet. 2. If no match is found, then the packet is discarded and an error message is generated. 3. If a match is found, further processing is determined by the first matching entry in the SPD. If the policy for this packet is discard, then the packet is discarded. If the policy is bypass, then there is no further IPsec processing. The packet is forwarded to the network for transmission. 4. If the policy is protect, then a search is made of the SAD for a matching entry. If no entry is found, then IKE is invoked to create an SA with the appropriate keys, and an entry is made in the SA. 5. The matching entry in the SAD determines the processing for this packet. Either encryption, authentication, or both can be performed, and either transport or tunnel mode can be used. The packet is then forwarded to the network for transmission. Processing model for inbound packets. The figure highlights the main elements of IPsec processing for inbound traffic. An incoming IP packet triggers the IPsec processing. The following steps occur. 1. IPsec determines whether this is an unsecured IP packet or one that has ESP or AH headers by examining the IP protocol field in IP version 4 or examining the next header field in IP version 6. 2. If the packet is secured, then IP searches the SAD. If no match is found, the packet is discarded. Otherwise, IPsec applies the appropriate ESP or AH processing. Then the IP header is processed and stripped off, and the packet body is delivered to the next higher layer, such as TCP. If the packet is unsecured, IPsec searches the SPD for a match to this packet. If the first matching entry has a policy of bypass, the IP header is processed and stripped off, and the packet body is delivered to the next higher layer, such as TCP. If the first matching entry has a policy of protect or discard, or if there is no matching entry, the packet is discarded. ESP packet format. The figure shows the top-level format of an ESP packet. It contains the following fields. Security parameters index, which is 32 bits, identifies a security association. Sequence number, 32 bits. A monotonically increasing counter value. This provides an anti-replay function, as discussed for AH. Payload data, which is a variable length. This is a transport level segment, transport mode, or IP packet tunnel mode that is protected by encryption. Padding, which can be from 0 to 255 bytes, and the purpose of this field is discussed later. Pad length, 8 bits, indicates the number of pad bytes immediately preceding this field. Next header, 8 bits, identifies the type of data contained in the payload data field by identifying the first header in that payload. For example, an extension header in IP version 6, or an upper layer protocol such as TCP. Integrity check value, variable length. A variable length field which must be an integral number of 32-bit words that contains the integrity check value computed over the ESP packet minus the authentication data field. When any combined mode algorithm is employed, the algorithm itself is expected to return both decrypted plain text and a pass-fail indication for the integrity check. For combined mode algorithms, the ICV that would normally appear at the end of the ESP packet when integrity is selected may be omitted. When the ICV is omitted and integrity is selected, It is the responsibility of the combined mode algorithm to encode within the payload data an ICV equivalent means of verifying the integrity of the packet. Two additional fields may be present in the payload. An initialization value, IV, or nonce is present if this is required by the encryption or authenticated encryption algorithm used for ESP. If tunnel mode is being used, then the IPsec implementation may add traffic flow confidentiality, TFC, padding after the payload data and before the padding field, as explained subsequently. Encapsulating security payload, ESP. The payload data, padding, pad length, and next header fields are encrypted by the ESP service. If the algorithm used to encrypt the payload requires cryptographic synchronization data, such as an initialization vector, IV, then these data may be carried explicitly at the beginning of the payload data field. If included, an IV is usually not encrypted, even though it is referred to as being part of the ciphertext. An ICV field is optional. It is present only if the integrity service is selected and is provided by either a separate integrity algorithm or a combined mode algorithm that uses an ICV. The ICV is computed after the encryption is performed. This order of processing facilitates rapid detection and rejection of replayed or bogus packets by the receiver prior to decrypting the packet, hence potentially reducing the impact of denial of service attacks. It also allows for the possibility of parallel processing of packets at the receiver. That is, decryption can take place in parallel with integrity check-in. Note that because the ICV is not protected by encryption, a keyed integrity algorithm must be employed to compute the ICV. The padding field serves several purposes. If an encryption algorithm requires the plaintext to be a multiple of some number of bytes, for example, multiple of a single block for a block cipher, the padding field is used to expand the plaintext, consisting of the payload data, padding, pad length, and next header fields to the required length. The ESP format requires that the pad length and next header fields be right aligned within a 32-bit word. Equivalently, the ciphertext must be an integer multiple of 32 bits. The padding field is used to assure this alignment. Additional padding may be added to provide partial traffic flow confidentiality by concealing the actual length of the payload. Anti-replay mechanism. A replay attack is one in which an attacker obtains a copy of an authenticated packet and later transmits it to the intended destination. The receipt of a duplicate authenticated IP packet may disrupt service in some way or have some other undesired consequence. The sequence number field is designed to thwart such attacks. First, we discuss sequence number generation by the sender, and then we look at how it is processed by the recipient. When a new SA is established, the sender initializes a sequence number counter to 0. Each time that a packet is sent on this SA, the sender increments the counter and places the value in the sequence number field. Thus, the first value to be used is 1. If anti-replay is enabled, which is the default, the sender must not allow the sequence number to cycle past 2 to the 32nd, -1, back to 0. Otherwise, there would be multiple valid packets with the same sequence number. If the limit of 2 to the 32 minus 1 is reached, the sender should terminate this SA and negotiate a new SA with a new key. Because IP is a connectionless, unreliable service, the protocol does not guarantee that packets will be delivered in order and does not guarantee that all packets will be delivered. Therefore, the IPsec authentication document dictates that the receiver should implement a window of size W with a default of W equals 64. The right edge of the window represents the highest sequence number N so far received for a valid packet. For any packet with a sequence number in the range from N minus W plus 1 to N that has been correctly received, i.e. properly authenticated, the corresponding slot in the window is marked. Inbound processing proceeds as follows when a packet is received. 1. If the received packet falls within the window and is new, the MAC is checked. If the packet is authenticated, the corresponding slot in the window is marked. 2. If the received packet is to the right of the window and is new, the MAC is checked. If the packet is authenticated, the window is advanced so that the sequence number is the right edge of the window, and the corresponding slot in the window is marked. If the received packet is to the left of the window, or if authentication fails, the packet is discarded. This is an auditable alert, an event. Transport mode versus tunnel mode encryption. The figure shows two ways in which the IPsec ESP service can be used. In the upper part of the diagram, encryption and optionally authentication is provided directly between two hosts. The bottom part of the figure shows how tunnel mode operation can be used to set up a virtual private network. In this example, an organization has 4 private networks interconnected across the internet. Hosts on the internal networks use the internet for transport of data, but do not interact with other internet-based hosts. By terminating the tunnels at the security gateway to each internal network, the configuration allows the host to avoid implementing the security capability. The former technique is supported by a transport mode SA, while the latter technique uses a tunnel mode SA. In this section, we look at the scope of ESP for the two modes. The considerations are somewhat different for IP version 4 and 6. We use the packet formats of the figure as a starting point. Scope of ESP encryption and authentication. Transport mode ESP is used to encrypt and optionally authenticate the data carried by IP, for example, a TCP segment, as shown in the figure. For this mode using IP version 4, the ESP header is inserted into the IP packet immediately prior to the transport layer header, for example, TCP, UDP, and ICMP. And an ESP trailer, including padding length, the next header fields, or padding, is placed after the IP packet. If authentication is selected, the ESP authentication data field is added after the ESP trailer. The entire transport level segment plus the ESP trailer are encrypted. Authentication covers all of the ciphertext plus the ESP header. In the context of IP version 6, ESP is viewed as an end-to-end payload. That is, it is not examined or processed by intermediate routers. Therefore, the ESP header appears after the IP version 6 base header and the next hop-by-hop routing and fragment extension headers. The destination option extension header could appear before or after the ESP header, depending upon the semantics desired. For IP version 6, encryption covers the entire transport level segment plus the ESP trailer plus the destination options extension header if it occurs after the ESP header. Again, authentication covers the ciphertext plus the ESP header. Transport mode operation may be summarized as follows. 1. At the source, the block of data consisting of the ESP trailer plus the entire transport layer segment is encrypted, and the plain text of this block is replaced with its ciphertext to form the IP packet for transmission. Authentication is added if this option is selected. 2. The packet is then routed to the destination. Each intermediate router needs to examine and process the IP header plus any plain text IP extension headers, but does not need to examine the ciphertext. 3. The destination node examines and processes the IP header plus any plain text IP extension headers. Then, on the basis of the SPI in the ESP header, the destination node decrypts the remainder of the packet to recover the plaintext transport layer segment. Transport mode operation provides confidentiality for any application that uses it, thus avoiding the need to implement confidentiality in every individual application. One drawback to this mode is that it is possible to do traffic analysis on the transmitted packets. Tunnel mode ESP is used to encrypt an entire IP packet. For this mode, the ESP header is prefixed to the packet, and then the packet plus the ESP trailer is encrypted. This method can be used to counter traffic analysis. Because the IP header contains the destination address and possible source routing directives and hop-by-hop option information, it is not possible simply to transmit the encrypted IP packet prefixed by the ESP header. Intermediate routers would be unable to process such a packet. Therefore, it is necessary to encapsulate the entire block, ESP header plus ciphertext plus authentication data if present, with a new IP header that will contain sufficient information for routing, but not for traffic analysis. Whereas the transport mode is suitable for protecting connections between hosts that support the ESP feature, the tunnel mode is useful in a configuration that includes a firewall or other sort of security gateway that protects a trusted network from external networks. In this latter case, encryption occurs between an external host and the security gateway, or between two security gateways. This relieves hosts on the internal network of the processing burden of encryption and simplifies the key distribution task by reducing the number of needed keys. Further, it thwarts traffic analysis based on ultimate destination. Protocol operation for ESP. Please pause and review this slide. Combining security associations. An individual SA can implement either the AH or ESP protocol, but not both. Sometimes a particular traffic flow will call for the services provided by both AH and ESP. Further, a particular traffic flow may require IPsec services between hosts and, for that same flow, separate services between security gateways, such as firewalls. In all of these cases, multiple SAs must be employed for the same traffic flow to achieve the desired IPsec services. The term security association bundle refers to a sequence of SAs through which traffic must be processed to provide a desired set of IPsec services. The SAs in a bundle may terminate at different endpoints or at the same endpoints. Security associations may be combined into bundles in two ways. Transport adjacency refers to applying more than one security protocol to the same IP packet without invoking tunneling. This approach to combining AH and ESP allows for one level of combination. Further nesting yields no added benefit since the processing is performed at one IPsec instance, the ultimate destination. Iterated tunneling refers to the application of multiple layers of security protocols affected through IP tunneling. This approach allows for multiple levels of nesting, since each tunnel can originate or terminate at a different IPsec site along the path. The two approaches can be combined, for example, by having a transport SA between hosts travel part of the way through a tunnel SA between security gateways. One interesting issue that arises when considering SA bundles is the order in which authentication and encryption may be applied between a given pair of endpoints and the ways of doing so. ESP with authentication option. Encryption and authentication can be combined in order to transmit an IP packet that has both confidentiality and authentication between hosts. We look at several approaches. One approach is illustrated in the figure. In this approach, the user first applies ESP to the data to be protected and then appends the authentication data field. There are actually two subcases. Transport mode ESP. Authentication and encryption apply to the IP payload delivered to the host, but the IP header is not protected. Tunnel mode ESP. Authentication applies to the entire IP packet delivered to the outer IP destination address, for example, firewall, and authentication is performed at that destination. The entire inner IP packet is protected by the privacy mechanism for delivery to the inner IP destination. For both cases, authentication applies to the ciphertext rather than the plain text. Transport adjacency. Another way to apply authentication after encryption is to use two bundled transport SAs, with the inner being an ESP SA and the outer being an AH SA. In this case, ESP is used without its authentication option. Because the inner SA is a transport SA, encryption is applied to the IP payload. The resulting packet consists of an IP header and possibly an IP version 6 header extension, followed by an ESP. AH is then applied in transport mode so that authentication covers the ESP plus the original IP header and extensions, except for mutable fields. The advantage of this approach over simply using a single ESP SA with the ESP authentication option is that the authentication covers more fields, including the source and destination IP addresses. The disadvantage is the overhead of two SAs versus one SA. Transport tunnel bundle. The use of authentication prior to encryption might be preferable for several reasons. First, because the authentication data are protected by encryption, it is impossible for anyone to intercept the message and alter the authentication data without detection. Second, it may be desirable to store the authentication information with the message at the destination for later reference. It is more convenient to do this if the authentication information applies to the unencrypted message. Otherwise, the message would have to be re-encrypted to verify the authentication information. One approach to applying authentication before encryption between two hosts is to use a bundle consisting of an inner AH transport SA and an outer ESP tunnel SA. In this case, authentication is applied to the IP payload plus the IP header and extensions, except for mutable fields. The resulting IP packet is then processed in tunnel mode by ESP. The result is that the entire authenticated inner packet is encrypted and a new outer IP header and extensions is added. Basic combinations of security associations. The IPsec architecture document lists 4 examples of combinations of SAs that must be supported by compliant IPsec hosts. For example, workstations or servers, or security gateways, firewalls or routers. These are illustrated in the figure. The lower part of each case in the figure represents the physical connectivity of the elements. The upper part represents logical connectivity via one or more nested SAs. Each SA can be either AH or ESP. For host-to-host SAs, the mode may be either transport or tunnel. Otherwise, it must be tunnel mode. Internet Key Exchange. The key management portion of IPsec involves the determination and distribution of secret keys. A typical requirement is 4 keys for communication between 2 applications. Transmit and receive pairs for both integrity and confidentiality. The IPsec architecture document mandates support for 2 types of key management. Manual. A system administrator manually configures each system with its own keys and with the keys of other communicating systems. This is practical for small, relatively static environments. Automated. An automated system enables the on-demand creation of keys for SAs and facilitates the use of keys in a large distributed system with an involving configuration. ISA-KMP Oakley. The default automated key management protocol for IPsec is referred to as ISA-KMP Oakley and consists of the following elements. Oakley Key Determination Protocol. Oakley is a key exchange protocol based on the Diffie-Hellman algorithm, but providing added security. Oakley is generic in that it does not dictate specific formats. Internet Security Association and Key Management Protocol, ISA-KMP. ISA-KMP provides a framework for Internet key management and provides the specific protocol support, including formats for negotiation of security attributes. ISA-KMP by itself does not dictate a specific key exchange algorithm. Rather, ISA-KMP consists of a set of message types that enable the use of a variety of key exchange algorithms. Oakley is the specific key exchange algorithm mandated for use with the initial version of ISA-KMP. In IKE version 2, the terms Oakley and ISA-KMP are no longer used, and there are significant differences from the use of Oakley and ISA-KMP in IKE version 1. Nevertheless, the basic functionality is the same. Features of IKE key determination. The IKE key determination algorithm is characterized by 5 important features. 1. It employs a mechanism known as cookies to thwart clogging attacks. 2. It enables the two parties to negotiate a group. This is, in essence, specifies the global parameters of the Diffie-Hellman key exchange. 3. It uses nonces to ensure against replay attacks. 4. It enables the exchange of Diffie-Hellman public key values. 5. It authenticates the Diffie-Hellman exchange to thwart man-in-the-middle attacks. IKE exchanges. The IKE version 2 protocol involves the exchange of messages in pairs. The first 2 pairs of exchanges are referred to as the initial exchanges. In the first exchange, the 2 pairs exchange information concerning cryptographic algorithms and other security parameters they are willing to use, along with nonces and Diffie-Hellman values. The result of this exchange is to set up a special SA called the IKE SA. The SA defines parameters for a secure tunnel between the peers over which subsequent message exchanges take place. Thus, all subsequent IKE message exchanges are protected by encryption and message authentication. In the second exchange, the 2 parties authenticate one another and set up a first IPsec SA to be placed in the SADB and used for protecting ordinary communications between the peers. Thus, 4 messages are needed to establish the first SA for general use. The child creation exchange can be used to establish further SAs for protecting traffic. The informational exchange is used to exchange management information, IKE version 2 error messages, and other notifications. IKE formats. The figure shows the header format for an IKE message. It consists of the following fields. Initiator SPI, which is 64 bits. A value chosen by the initiator to identify a unique IKE security association. Responder SPI, which is 64 bits. A value chosen by the responder to identify a unique IKE SA. Next payload, which is 8 bits, indicates the type of the first payload in the message. Payloads are discussed in the next subsection. Major version, 4 bits, indicates major version of IKE in use. Minor version, 4 bits, indicates minor version in use. Exchange type, which is 8 bits, indicates the type of exchange. These are discussed later in this section. Flags, 8 bits, indicate specific options set for this IKE exchange. 3 bits are defined so far. The initiator bit indicates whether this packet is sent by the SA initiator. The version bit indicates whether the transmitter is capable of using a higher major version number than the one currently indicated. The response bit indicates whether this is a response to a message containing the same message ID. Message ID, which is 32 bits, used to control retransmission of lost packets and matching of requests and responses. Length, 32 bits. Length of the total message, header plus all payloads in octets. All IKE payloads begin with the same generic payload header shown in the figure. The next payload field has a value of 0 if this is the last payload in the message. Otherwise, its value is the type of the next payload. The payload length field indicates the length in octets of this payload, including the generic payload header. The critical bit is 0 if the sender wants the recipient to skip this payload, and if it does not understand the payload type code in the next payload field of the previous payload. It is set to 1 if the sender wants the recipient to reject this entire message if it does not understand the payload type. IKE payload types. The table summarizes the payload types defined for IKE and lists the fields or parameters that are part of each payload. The SA payload is used to begin the establishment of an SA. The payload has a complex hierarchical structure. The payload may contain multiple proposals. Each proposal may contain multiple protocols. Each protocol may contain multiple transforms, and each transform may contain multiple attributes. These elements are formatted as substructures within the payload as follows. Proposal. This substructure includes a proposal number, a protocol ID, for example, AH, ESP, or IKE, an indicator of the number of transforms, and then a transform substructure. If more than one protocol is to be included in a proposal, then there is a subsequent proposal substructure with the same proposal number. Transform. Different protocols support different transform types. The transforms are used primarily to define cryptographic algorithms to be used with a particular protocol. Attribute. Each transform may include attributes that modify or complete the specification of the transform. An example is key length. The key exchange payload can be used for a variety of key exchange techniques, including Oakley, Diffie-Hellman, and the RSA-based key exchange used by PGP. The key exchange data field contains the data required to generate a session key and is dependent upon the key exchange algorithm used. The identification payload is used to determine the identity of communicating peers and may be used for determining authenticity of information. Typically, the ID data field will contain an IP version 4 or 6 address. The certificate payload transfers a public key certificate. The certificate encoding field indicates the type of certificate or certificate-related information, which may include the following. PKCS number 7 wrapped X509 certificate. PGP certificate. DNS signed key. X509 certificate, the signature. X509 certificate, key exchange. Kerberos tokens. Certificate revocation list, CRL. Authority revocation list, ARL. SPKI certificate. At any point in an IKE exchange, the sender may include a certificate request payload to request the certificate of the other communicating entity. The payload may list more than one certificate type that is acceptable and more than one certificate authority that is acceptable. The authentication payload contains data used for message authentication purposes. The authentication method types so far defined are RSA digital certificate signature, shared key message integrity code, and DSS digital signature. The nonce payload contains random data used to guarantee liveness during an exchange and protect against replay attacks. The notify payload contains either error or status information associated with this SA or this SA negotiation. The following table lists the IKE notify messages. The delete payload indicates one or more essays that the sender has deleted from its database and that therefore are no longer valid. The vendor ID payload contains a vendor-defined constraint. The constraint constant is used by vendors to identify and recognize remote instances of their implementations. This mechanism allows a vendor to experiment with new features while maintaining backward compatibility. The traffic selector payload allows peers to identify packet flows for processing by IPsec services. The encrypted payload contains other payloads in encrypted form. The encrypted payload format is similar to that of ESP. It may include an IV if the encryption algorithm requires it, and if an ICV is authentication as selected. The configuration payload is used to exchange configuration information between IKE peers. The Extensible Authentication Protocol, EAP, payload allows IKE essays to be authenticated using EAP, which was discussed in Chapter 5. Cryptographic suites for IPsec. The IPsec version 3 and IKE version 3 protocols rely on a variety of types of cryptographic algorithms. As we have seen in this book, there are many cryptographic algorithms of each type, each with a variety of parameters such as key size. To promote interoperability, two RFCs define recommended suites of cryptographic algorithms and parameters for various applications. RFC 4308 defines two cryptographic suites for establishing virtual private networks. Suite VPN-A matches the commonly used corporate VPN security used in older IKE version 1 implementations at the time of issuance of IKE version 2 in 2005. Suite VPN-B provides stronger security and is recommended for new VPNs that implement IPsec version 3 and IKE version 2. The table lists the algorithms and parameters for the two suites. There are several points to note about these two suites. Note that for symmetric cryptography, VPN-A relies on SSS and HMAC, while VPN-B relies exclusively on AES. Three types of secret key algorithms are used. Encryption. For encryption, the cipher block chaining CBC mode is used. Message authentication. For message authentication, VPN-A relies on HMAC with SHA-1, with the output truncated to 96 bits. VPN-B relies on a variant of CMAC with the output truncated to 96 bits. Pseudorandom function. IK version 2 generates pseudorandom bits by repeated use of the MAC used for message authentication. RFC 6379 defines four optional cryptographic suites that are compatible with the United States National Security Agency's Suite B specifications. In 2005, the NSA issued Suite B, which defined the algorithms and strength needed to protect both sensitive but unclassified SBU and classified information for use in its cryptographic modernization program. The four suites defined in RFC 6379 provide choices for ESP and IKE. The four suites are differentiated by the choice of cryptographic algorithm strengths and a choice of whether ESP is to provide both confidentiality and integrity or integrity only. All of the suites offer greater protection than the two VPN suites defined in RFC 4308. The table lists the algorithms and parameters for the two suites. A's with RFC 4308, 3 categories of secret key algorithms are listed. Encryption. For ESP, authenticated encryption is provided using the GCM mode with either 128-bit or 256-bit AES keys. For IKE encryption, CBC is used as it was for the VPN suites. Message authentication. For ESP, if only authentication is required, then GMAC is used. As discussed in Chapter 12, GMAC is simply the authentication portion of the GMC. For IKE, message authentication is provided using HMAC with one of the SHA-3 hash functions. Pseudorandom function. As with the VPN suites, IKE version 2 in these suites generates pseudorandom bits by repeated use of the MAC used for message authentication. For the Diffie-Hellman algorithm, the use of elliptic curves module a prime is specified. For authentication, elliptic curve digital signatures are used. The original IKE version 2 documents used RSA-based digital certificates and signatures. Equivalent or greater strength can be achieved using ECC with fewer bits. And we have a summary. We've talked about IP security and given you an overview. We've talked about the security policy, the cryptographic suites, the encapsulating security payload, combining security associations, internet key exchange. So please take a moment and review the details on this slide. Thanks for listening. Bye from Teacher Todd.